This project is called Detecting Ships from Satellite Images. As you all know, there was a boom in the marine industry, which led to an increase in the number of ships in the sea, and that led to an increase in the much higher trafficking in the sea and illegal fishing and accidents in the sea. So we think that to be able to monitor these ships and to be able to identify their location and their precise bounding box segmentation is important to be able to autonomously detect those ships. The data and its features, we collected data from Kaggle, and the data was sponsored from Airbus, and the initial data set was around like 180,000 images for the training and 50,000 for testing, and the goal was to be able to find the bounding box of these ships. Data pre-processing, we had the original images and the corresponding masks for each occurring ship. So the mask was in an encoded format, so we need to transform it and decode it into an image to be able to use it in our training. And we balanced the class by 6:40 samples having the ratio of 6:40 with samples having no ships to ships. And below we can see a sample image from the CSV file where the pixels are encoded. And you can see this is like the unmasked versions of the encoded pixels. So the dataset was highly imbalanced, which like out of 180,000 images, like number of images without ships was like around 140,000, and number of images with ships was like 40,000, and we reduced this to 110,000 total images, having 66,000 images with ships and 42,000 images with no ships. And we use Keras image generator and custom data augmentation function, perform normalization by dividing each pixel by 255, and we augmented images, flipping, increasing the brightness, and mirroring the images because that's important for a UNet model to learn good. And that's the size that we fill in the UNet model. So input is the 3 channel and the up is the 1 channel. So which means like it's either black or white. Because of the semantic segmentation, we are doing this in UNet. And as you can see on the top right hand side, how the semantic segmentation works, whereas there's a background, the bicycle, and the man. So you need to be able to detect the edges and fill everything according to that class. So this is called pixel level image classification. The CN architecture is used to extract features in the form of UNet. So this CN architecture allows us to localize an image and look at its features in depth as it increases the number of channels and decreases the dimension. So, and also the UNet model is full convolutional network, so that the input can be any images having any size, and the output will be an image as well. And UNet consists of contracting, bottleneck, and expanding paths, which is called also encoding and decoding paths as well. This is the UNet architecture from the original paper named UNet Convolution Networks for Biomedical Image Segmentation. As you can see, the encoder part extracts the features of the corresponding receptive fields of the filters, and then in the decoder part, you see the transposed convolution followed by concatenation coming from the same block for the encoding from the encoding path, which allows us to be able to not to lose the local information of what's present in the image to be able to retrieve the image back. So this is our initial architecture that we use. It's pretty same as the UNet model, but we added batch normalization in the end and tuned the hyperparameters. So in this model, the convolution layers are used to extracting the features, and transposed convolution layers are used with concatenation with the skip connection with the down blocks to be able to retrieve the localization position information of the images. In our model, each image was 768 by 768, and the encoder path reduces to 96 by 96 using max pooling, and the deconvolution path in the decoder path converts it back to the 768 by 768 and decreases the channels until 1 using convolutional rails, and increases the image dimension by 2 using the convolutional layers. So if we want to go through the layers of the UNet, we can see the contracting path consists of two 3x3 convolutions with stride 1 and uses a relay activation, and two 2x2 max pooling with stride 2 for downsampling. And the bottleneck layer is just to pass the information to the encoding path. An expanding path is the upsampling path. In the upsampling path, simply is the transpose convolution and followed by a convolution, and concatenation with the corresponding feature map from the downsampling path. Advantages of the UI network compared to patching, which is another convolutional semantic image segmentation solution, which is computation much more efficient, and you can input any image, use any image as an input. There's no dense layers, and it's considerably much more faster, memory efficient and faster than the other semantic segmentation networks with dense layers. Metrics and loss functions. We use intersection or union in our loss function, involved in computing the accuracy of our loss models. As you can see on the below, there's like a graph showing how it's calculated. And there's also a dice loss function, which is kind of similar to the U of I, which is considered as a variant of U of I. So this was the initial model that I presented to you, and these were the results that we got from the initial model. You can see that the model was able to detect the edges, but it's not able to fill out the boxes. So it's able to regenerate the image, but cannot fill the boxes entirely. Also, when there's noise present in the model just regenerates the image back in terms of the pixel intensities rather than classifying, learning what ship is. In order to tackle this issue, we increase the number of filters, decreasing the image size, increasing the number of channels, and adding batch normalization after each up and down block. We get the corresponding results, where we can see that our predicted bounding box is actually better than the actual bounding box. So this was a quite good improvement in the results. And you can see in this image as well, the same thing, which our model outperforms is the actual bounding box. And also, when you have a noise in the image, where the original image doesn't have any shapes, and it's like noisy and like a background, or it can be like a land or something. There is no shapes, and the actual bounding box is black, and our predicted bounding box is also black. It just has a small white instance, like maybe 1 pixel there, and other than that, it was able to predict pretty good. So the final model was able to identify the ships pretty well, but one of the bad things about this model was the checkerboard artifact, which is resulted by overlapping of deconvolutional layers. We weren't able to solve this issue, but in the further developing this model further, we're thinking to adding a nearest neighbor interpolation instead of having a deconvolutional block, and then having a convolution to learn those features better, and then getting rid of these checkerboard overlapping. For further, you can go to GitHub and check the code and ask us if you have any questions about the model and if you need help about a similar problem. Thank you for listening.